Hello everyone, my name is Heath Rachadia and in this video I'll be showing you the simulation and visualizations of the different ML concepts. So these simulations are on browser only, so no need to download or install any software. So let's look at the website of the simulations. So this is the site name. You can note down or you can open in your browser and play with the basic machine learning algorithms to deep learning algorithms. So in this video, I'll be showing you the simulation for these six concepts. Okay, so let's look at the first concept. So first concept is about simple linear regression. So let's look at what is the first linear regression is. Okay. So linear regression is a statistical method used to model the relationship between a dependent variable and one or more independent variables. So it basically predicts the value of dependent variable as a linear combination of the dependent variable. And the equation for linear regression is y is equal to beta, or you can take alpha only. So beta 0 plus beta 1x. So in that y is our dependent variable and x is our y is our dependent variable and x is our independent variable. So we are predicting the value of y, and then beta 0 is the intercept and beta 1 is the slope. So these betas are the coefficients. Okay, so the applications of the linear regression is to predict the numerical outcomes. Like we can say we can use this in house price predictions, then sales figure, and we can also use linear regression for identifying the trends and patterns in data. Okay, so in the graph canvas, you can see there are different values are plotted, and this is the noise controller. So noise is represent the randomness or error in the data, and increasing the noise will result in less predictable and less smooth data prediction. So as you can see, the data values will be very randomness. So let's take the default value only, and by pressing the any of the place in the graph, we can put the values. So you can also put the values if you want. So let's let's start the simulation. So we can see it generating the best fit line for our model, and in analysis section we can see the approximated function, train MSC and test MSC. So this train MSC and test MSC are the measures of the error in regression model, and it helps to assess how well our model fits and data generate our model fits the data and generalize to unseen data. Okay, so for MSC is stands for mean square error, and it measures the average squared difference between the predicted value and actual value. And there are given the train MSC and test MSC. So train MSC is always lower than the test MSC, and when we are having the significant gap between train MSC and test MSC, signals potential issue. When the gap is high or significant, it signals us that model is having the potential issue with model complexity. Okay, so this is the all about the simple linear regression simulation. Uh, Now we can move to the non-linear regression. So this is also the type of linear regression, but in this we are not having the linear equations like y is equal to beta 0 plus beta 1 x something. Instead of that, it follows a non-linear function form such as y is equal to f of x beta plus error. Okay. In the simulation, we can see there are given one parameter, except noise is degree. So this degree is refers to the highest power of independent variable in the equation. So when the degree is low, it gives us simple smooth curves that may underfit the data if the relationship is complex. And if we are keeping degree high, then it will giving us the complex curve that can fit uh, the pattern but may overfit or capturing the noise in the data instead of true underlying relationship. Okay, so the advantages of the nonlinear regressions are it is flexible, so it can capture the complex and real world applications or relationships, and it is the more accurate than the linear regression. So when the relationship is inherently non-linear regression often performs better. Okay? And the applications of the non-linear regression is we can use in the biology, like we can model the population growth. Then we can model the returns on exponential growth in economics. Then we can also use this in physics for describing the physical phenomena like radioactive delay or hard transfer, etc. And we can also use for machine learning for underlying relationship in neural networks and decision trees. So now let's start the simulation, and we can see there is given best fit line which is not linear in nature. So this is the main difference between linear regression and non-linear regression. So for non-linear data set, we can use the non-linear regression, and these parameters are also same as the linear regression. Now let's look at the next, which is the decision tree classifier. So this is the classification algorithm. First of all, let's understand what is the decision tree. So decision tree is a supervised machine learning algorithm used for both classification and regression tasks. It represents a decision and possible consequence, consequences structure in the form of tree-like graph. So it is an intuitive and interpretable reassembling flow chart where each node is represent a decision point. So what is the structure of decision tree? So there is one root node which is the topmost node in the tree, and it represents the entire data set is a starting point for splitting. And second is the internal nodes. The internal nodes represents the decision points based on the certain features and threshold. So each internal node splits the data into subsets based on the feature conditions. Okay. And third is the leaf node. So leaf node represents the final output, and no further splitting occurs beyond these nodes. And fourth is the branches. So branches represents the outcome of decision at each node, which is leading to the next node. So this is the structure of decision tree. Then how it works. Okay, so each node, the data is split into subsets based on the feature and threshold value that optimize the splitting criterion. Okay, so this is about the decision tree. Then how the decision tree is selecting the feature for classification purpose. So for that we are having two options. Like first is Gini impurity. It measures how often a randomly chosen element would be incorrectly classified. And then we have entropy or information gain. It measures the reduction in uncertainty after the splitting. Okay, so as I mentioned earlier, this can be used in classification and regression purpose. So in classification purpose, the leaf node output the majority class of the samples in that node. And in regression, the leaf node output the mean or median of the target variable in that node. Okay, so now the advantages of the decision tree is it is easy to understand and visualize. Then non-linear relationships, like it can capture the complex pattern in data. Then feature importance, it highlights the most important feature used in the decision. And then it can handle the mixed data type, like decision tree can handle both numerical and categorical data. Then what are the applications or where we can use the decision tree classifier in real world? So we can use the decision tree in spam detection, fraud detection, and medical diagnosis. Other than that, in regression purpose, we can use this for predicting house price and stock market trends. And in feature selection, we can use for identifying important variables in dataset. So now we can see in simulation there is one extra parameter is given, which is smooth. So smooth controls the thickness of split and smoothing transition between splits or preventing overlay sharp boundaries. Okay, so now let's start the simulation and see the output. So yeah, you can see this is giving the output in classification. So this is only for classification. So you can see a majority of blue values are in this portion. So this is one class and this is other class. And the test accuracy is 50% and train accuracy is 60%. And this is the data points are given is a type of Gaussian. We can also use the different types of data types. Like when we are resetting, it will giving us the XOR data type. So this will leading us to different types of classifications. Okay, so this is all about the decision tree classifier simulator. Now let's look at the support vector machine. So let's understand what is the support vector machine. So support vector machine is a supervised machine learning algorithm used for both classification and regression tasks. So it is particularly well suited for binary classification problem, where it aims to find the optimal hyperplane that separates the data points from different classes with maximum margins. Okay. This SVM is having advantages of effective in high dimension. So we can say that by its process, we can say that the SVM works well in the high dimensional data, where the numerator of features is the larger than the number of samples, and it is robust to overfitting. So especially when we are using the appropriate kernel and regularization. At that time, it is very much robust for overfitting, and it can handle the non-linear relationships. So, in the kernel trick, allows SVM to model the complex and non-linear relationships. When we can use the SVM in real life applications, like when we have to do the classification for image recognition, then for spam detection and sentiment analysis, at that time we can use the SVM. Then for regression purpose, it is called SVR, so support vector regression. So we can use this for predicting continuous outcomes. Then we can use for anomaly detection, like we can use for detecting fraud or rare events. And we can also use this for medical diagnosis. Okay. Uh, so in the simulation, you can see there is one option is given, which is kernel. So this is basically a function which define how the SVM algorithm maps the data into higher dimensional space to make it linearly separable. So it determines the shape of the decision boundary. Okay, so the kernel is used for this purpose, and in this they are given only two kernel, but there are commonly used kernel are four. So one is linear, then polynomial, then RBF, which is radial basis function, and then fourth is sigmoid kernel. So in this we are using the RBF because our data is non-linear, and also this RBF is widely used. So for this demonstration purpose, we are also using the RBF kernel. Then the second option given is cost. So the cost parameter controls the trade-off between maximizing the margin and minimizing the classification errors. So when we are putting the value of cost to low, at that time it allows for a wider margin by tolerating some misclassified point, and it will lead us to simpler model than that generalized better but may underfit. Then for high cost value, it penalized the misclassification heavily and leading to narrower margin, and it will focus on correctly classified training points, but it risks for overfitting. So in brief, we can say the cost is a regularization parameter that balance the model complexity and error. Okay. So this is for the SVM. Now there is one option other is given gamma. So the gamma parameter is applies specifically to the RBF kernel and sometimes the polynomial kernel also. So it controls the influence of individual data points on decision boundary. So when we are putting the gamma to a lower value, at that time, each data point has a large radius influence and produce a smoother, more generalized and decision boundary, but it may underfit when the gamma value is low. And when the gamma value is high, at that time, each data point has a small radius of influence, and it produces a very complex decision boundary, potentially overfitting to noise. Okay. So in short, we can say the gamma determines the flexibility of decision boundary in non-linear transformation. And in last, we have also smooth parameter. So The smooth parameter refers to the regularization for the decision boundary smoothness. It could control the level of granularity of or prevent the overfitting in high complex models. So, fully connected artificial neural network, also known as the dense neural network. So, this is about the support vector machine. Sorry, I started the explaining the ANN, but now let's let's see the simulation for support vector machine. So let's put all the values to the default and start the simulation. So you can see now this is not discrete classification. So it will give us this type of classification for spiral data types whose train accuracy is 100% and test accuracy is 99%. And you can also see the losses are very low. So this is performing very good for this type of data. And when we are putting it to the discrete, it will giving us this type of classification in which only this portion, which value has only this portion, it will be on the red class, and other all are in the blue class. Okay, so this is the difference between discrete and non-discrete. Okay, so non-discrete, these other portion are not defined, but in discrete, other person are comes under the red label. So uh, this is the about support vector machine. So now look at the other concept, which is artificial neural network or regression and classification both. So let's first look at the ANN for classification. Okay. So this is the simulation for ANN classification. So first of all, what is the uh, artificial neural network? So it is the also known the artificial neural network is also known as the dense neural network or fully connected. And it is a type of neural network where each neuron is one layer. Each neuron in one layer is connected to the every neuron in the next layer. So it can be the fully connected artificial neural network. And it can be used for regression and classification both, as we are saying that we are doing for both. And the structure for fully connected neural network, in that first we are having the input layer, which is the first layer in which it takes the input features from the data set, and the number of neurons correspond to the number of features in the data. Then the second part is the hidden layer. So it is a layers between the input and output layers. In that, the neurons in this layer are applied weight, biases, and activation functions to transform the input, and the number of hidden layers and neurons in each layer are hyperparameters that you can tune. And third is the output layer. So this is the final layer that produce the network's output. And in regression, a single neuron or multiple neuron is represented as output, and for classification, the number of neurons equals to the number of classes with output interpreted as possible or scores, possibilities or scores. Okay, so this is both for classification and regression. last is the fully connected layers. Okay. So I have mentioned in fully connected layer, each neuron receives input from every neuron in the previous layer. Then there is given different options optimizer. First is optimizer. So there is given multiple options for optimizer. So optimizer is the network update, or we can say that optimizer defines how the network update is weights and biases during the training to minimize the loss function. And it determines the direction and size of coach update in the parameter space. So the common optimizers are the SGD, which is given in the then Adam, then the ADM full form is the adaptation estimation, then RMS EROP, then Edgard, Ed Delta, and Adamax, and these all are given. So we are using the Adam only. So the Adam is combines the benefits uh, benefits of the SGD. So SGD is stochastic gradient descent, in which the it updates the weights using the gradient of the loss function. So it combines the SGD with adaptive learning rate and uses the both first order and second order moment estimates of gradients. Okay, then we are having second parameter is batch size. So batch size determines the number of samples used to compute gradients and update the model weight in each training set. So there are some types of batch size, but in this simulation there is given the scroller for putting the values in numerical form. Okay, so the common or typically range for batch size is 16 to 512, and it is depending on the data set size and memory constraint, but we can say the typical size range is uh, 16 to 512. When we are putting the small batch size, it will it will give us the faster updates, but noisy gradients and potentially unstable training is shown. And then for small batch size, it is often better generalization, but we can see there is slower convergence. Okay. And when we are having the large batch size, it will give us the smooth gradients and stable updates, but it requires the more memory and it may lead us to the overfit. And we are having another parameter is LR. This stands for learning rate. So learning rate controls the size of the steps. Optimizer takes in the parameter space during the training. So when we are putting the learning rate to low, the small step lead to slow coverage, and it helps us to avoid the overshooting the minimum. But but training can be time consuming or lower learning rate. And when the learning rate is high, the large steps can speed up the coverage. So, risk of the overshooting or oscillating around the minimum and falling to the converge. Then then the last option is given us is to network architecture. So Network architecture defines the structure of artificial neural network, including the number of layers and the number of neurons per layer. So there are given three layers. Okay, so we are taking three layers only, and there is also given the activation function which I already talked about it. So let's first take the default values and start the simulation. So it will start. Yeah, it will start it. So this will take time around 4 to 5 minutes for the classification. So you can see this is not the discrete. So and the data type is Gaussian, but we can see that it can be classified by linearly. And how many number of epochs are performed, that is also given, and we can see the train accuracy, test accuracy, and train and test loss for each epochs. And we can also see the loss curves for every epochs. Okay, so the red line is given for test epochs, and blue line is given for pineapple. So it is getting significantly down when the approaches are gradually increasing. This is about the uh, NN for classification. And when we are putting it to the discrete, it will give us the classification like this. Like below this portion, all the values are comes under this blue class, and above this portion, all the values are comes under the red. So this will take more time. So I can't show in the video because the video will get much longer. So you can simulate them and check the how many number of approaches are performed and the what is the accuracy and losses. Okay, and we can also see this for different types of classifications. Like this is I think this will giving us only quotient. Now, okay, this is giving spiral type. We can also classify using spiral data sets. But compared to the Gaussian data type, this will giving us the less accuracy and more loss. So you can see this will giving us only 60% accuracy in average. When the data set type is Gaussian, at that time we are getting the accuracy around 90 something. So this is about the classification of ANN. Now let's look at the last concept, which is artificial neural network or regression. So in this also there are given the same parameter as we are seeing in classification. But what is the difference? So in regression, we are getting the network output as continuous value or values if predicting the multiple output. Okay, and in the activation function, we can typically use the RLU or TANH in the hidden layer, and the output layer uses linear activation function. And in loss function, we are calculating the mean absolute error or mean square error, and also the other regression loss functions also, which can be used for only regression. Okay. So Uh, this is the all the parameters for regression purpose also. Now let's start the simulations. So when we are starting the simulations, you can see the best fit lines is generated. So this will also taking the much time. I have performed full simulations, so it will taking around uh, 400 something approaches. Oh, no, it will taking around 600 something approaches. So this is will taking more time. So you can perform the simulations on your devices and check the output for the different optimizer, different actuation functions. And you can also add the more networks for the higher complexity data sets. But I am using the default because it will generating the output within the short period of time. Okay, so that I can show in the video. We can see the train MSC, test MSC, and number of approaches are generated. So when the approaches are increasing, we are getting the good amount of mesh fit line, which is giving us the uh, low error between predicted value and original. So when the approaches are gradually increasing, we are able to see that the error is becoming error is becoming more and more less. So yeah, this is all about the simulations for machine learning concepts, and you can also note down the site for your learning purposes. And thank you. Thank you.